Hello everyone, welcome to the video lecture series of Internet of Things. In today's lecture, we are going to discuss topic NFC, Z-Wave, BLE, BACnet, Modbus protocols. I am Professor Swati Suresh Pawar. Before starting with today's lecture content, let us revise the contents of the previous lecture. In previous lecture, we discussed the WPN technologies for IoT, in which we discussed the ZigBee and HIRT. Now let us discuss the near field communication, that is NFC first. NFC is a short range wireless technology which combines contactless identification and interconnection technologies to provide communication between two devices. NFC can be used to transfer data like, that is not limited to, pictures, telephone numbers, MP3 files or digital authorization etc. between two devices, usually mobiles, that are NFC enabled, or between NFC devices, that is mobile, and RFID card, which are close to each other. NFC works on a frequency range of 13.56 MHz and provides data transmission rate up to 424 kilobytes per second with a range of nearly 10 centimeters. NFC has three main operating modes: passive modes, peer-to-peer mode, and active mode. Passive mode first, also known as card emulation mode. NFC devices acts like an existing contactless card in this mode, which can be readily used with existing systems that are using legacy NFC standards. For example, contactless payment system and ticketing system. Second is peer-to-peer mode. In this mode, two NFC devices can exchange data or information. As a target device or destination device, that is listener, uses its own power supply. The polling devices, that is the device which initiates the transmission, requires less power compared to the reader or writer mode. This mode is standardized on the ISO REC 18092 standard. Third is active mode, also called as read-writer mode. The NFC device is active and can read or write to NFC tags as well as passive RFID tags. The NFC Forum, which works on development and deployment of NFC, was established in the year 2004 by NXP, Nokia and Sony. The NFC Forum manages the interoperability of NFC with other devices using different manufacturer or technologies. NFC devices can talk to each other using three types of signaling technologies. Once the reader and tag makes contact, initially they try to communicate what technology that they can understand and transmit data with respect to the specific protocol. NFC signaling technology in brief. Table shows the NFC signaling technology, which shows the different NFC standard. Then shows the polling or it can listening. Then the moderation used for purpose, data rate that can be achieved. Then coding used and the carrier frequency for different NFC standards. Now let us discuss the Z-Wave. Z-Wave is a low power MAC protocol that has been used for IoT communication and especially for small commercial domain and smartphone. Z-Wave communicated using wireless technology aimed specifically for remote control applications. Z-Wave functions in the sub-gigahertz frequency range around 900 MHz. This band comes near to some cordless telephones and other consumer electronic devices but doesn't interfere with the Wi-Fi and other systems. Z-Wave has a range of about 30 meters and uses point-to-point communication. It can provide up to 75 to 100 meters without obstruction. Z-Wave ID appropriate for small messages in IoT application. For example, light control system, energy control system, wearable healthcare monitoring, etc. CSMA or CA is used as a consolation detection mechanism in Z-Wave and reliable transmission is provided using ACK mechanism. it's a collision. Z-Wave works on master-slave architecture where the master node controls the slaves, sends commands and also schedule of the whole network. Z-Wave uses a source-routed mesh network topology and can have one or more master primary nodes controllers which manages routing and security. But only one device can act as a master node at a time in a network. A device that can compile the routing table of the network can calculate route to the various nodes is called as a controller. Z-Wave network must have at least one master primary controller and can have up to 232 devices connected together. Primary collector contains description of the Z-Wave network and it also controls the outputs. Primary controller also assigns the network or home ID and node ID to the Z-Wave nodes during the network registration process. Secondary controller has the same network ID as the primary controller and is remain stationary as it has to maintain the routing tables. Using intermediate nodes for active routing, devices can communicate with each other devices and can avoid household obstacles or radio dead spots. Z-Wave uses network ID and node ID terms for identifying devices and networks, which is used for routing. Slave nodes do not contain routing tables but can have network maps which have information about routes to various nodes. Z-Wave network uses 32-bit unique identifier called the home ID to separate network from one another. Inclusion: the process of assigning the home ID and node ID to the slave devices is called as the inclusion in Z-Wave network formation. Primary controller first initiates the process of inclusion by activating the function button or command on the node. Once an uninitiated device is activated, the primary controller assigns it the home ID and node ID which start the processing of making that device a part of the Z-Wave network. Excluding: in this process, the previously assigned home ID and node ID in the process of inclusion is removed. Home ID and node ID is reset to 0 due to exclusion. The only exception to exclusion process is a controller. If a controller is excluded to home ID, reverts to the ID program while manufacturing. As shown in the figure, primary, master that is controller and secondary controller are handling 5 slave nodes. These nodes can be household applications like the fan, lights, etc. Figure shows a simple Z-Wave network. Now let us discuss the BLE, that is Bluetooth Low Energy. BLE, also known as Bluetooth Smart Works with Physical and MAC Layer, is a short-range communication protocol usually used for in-vehicle networking. BLE uses low energy because of which it has range 10 times less than the classic Bluetooth and its latency has reached 15 times. BLE uses a contention-less MAC having low latency and fast transmission for access control. BLE works on master-slave architecture and has two types of frames: adverting frames and data frames. Another adverting frames, it is used for network discovery. Slave sends the adverting frame on one or more of dedicated advertisement channels. Once dedicated to advertisement channels, slaves can connect with master nodes. To find the slaves and to connect them with master node senses advertisement channel. Once connection is established, master node manages the waking cycle and scheduling sequence of slave nodes. Nodes remain awake only when they are communicating with other node and go to sleep when they don't have any data to communicate. That saves their power. Other than connecting to slaves, advertising frames are also used for broadcasting the data for application which doesn't need the full connection. Once connection is made, data frame can be used for the actual data transfer, and the maximum data payload is 246 bytes only. As shown in the figure, BLE packet format remains the same for both advertising channels and the data channels. Message integrity check, that is MIC, is used as a part of the payload in data channels, that is PDU, to provide the security. Figure shows the BLE packet format with data channel PDU and the advertising channel PDU. Now let us discuss the BACnet protocol. The BACnet stands for Building Automation and Control Networks. BACnet targets industrial automation and control mechanisms. BACnet is an object-oriented protocol which views its implementation in the form of objects. BACnet protocol is defined by three basic characteristics. First is object, services, and properties. BACnet objects. BACnet object is an logical representation of the usable entity, which can be physical devices, analog input, that is temperature input, binary output, that is relay controllers, etc. BACnet currently has 30 object types, more under research. Some BACnet objects: access door, calendar, device, file, binary input, binary output, binary values, analog input, analog output, analog values, etc. Now the BACnet protocol. Device. All physical devices need to implement device object. The object identifier separates device on the BACnet network. File provides a file object that can be accessed using the file services. Calendar object provides list of dates, and access doors gives the object emulating an actual physical door, that is open and close. Such objects are available in BACnet, which can be effectively used for IoT-based applications. BACnet properties. The information about the BACnet objects are defined by its properties. Each of the BACnet object must have following three properties: object identifier, object name, object type. Object may have properties as per its specification and might not be found common in other objects. BACnet services. Services are nothing but actions that can be performed with the help of BACnet objects. Services such as read, write, input, output are available. Objects that provide services is a server, and the one that accesses the services is a client. An object can be a server, client, or both based on the application's requirement. The 5 classes of services provided by BACnets are: alarm and event services, file access services, object access services, remote device management services, virtual terminal services. First, alarm and event services. These sets of services provides event reporting to various activities. Alarm can be set for change of values event. This class has service like acknowledge alarm, confirm CO notification, unconfirmed COV notification, get alarm summary, get event information, etc. File access service. Read or write operation on the files is performed with this service. Only one operation is done at a time. Object access services. Set of services providing access to the object with services like read property, write property, create object, delete object, read property conditional, write property multiple, etc. Remote device management services. WHOIS MI service are used to identify objects over BACnet network, and remote devices management services can be used to remotely start, stop, manages. Device object initialization, vendor specific commands. Virtual terminal services allows the bidirectional exchange of character oriented data streams. Other example of services: confirm text messages, unconfirmed text messages, automatic read file, automatic write file, reinitialize devices, etc. Backnet objects properties. Example, table shows the name and value, object name, space temperature, object type is analog input, present value is 75, high limit is set to 80 and low limit is 60. Services can be used on condition of temperature is crossing the high or low value. Different services can be used based on application need. Now let us discuss the Modbus. Modbus is a serial communication protocol developed by a Modicon Inc. that is now Skinner Electric in 1979. Modbus is an application layer protocol which provides client-server communication to the devices connected via buses and the network. Modbus works on a top of serial communication standards like RS-232 and RS-442, RS-485. Modbus works with master-slave model. One master device initiates the transaction by generating query and sent to an individual slave address or broadcasted in the network. The slave devices work according to the query or return data generated as a result of query back to the master device. Modbus has two transmission modes that defines framing and bit encoding for messages to be transmitted on the network. American Standard Code for Information Interchange, that is ASCII code, transmission mode. Remote Terminal Unit, that is RTU, transmission mode. All nodes in the Modbus network have to use the same transmission mode and serial parameters to function properly. First is ASCII transmission mode and second is RTU transmission mode. ASCII transmission mode first. Coding system. One hexadecimal character is contained in each ASCII character of message. ASCII character 0 to 9 and A to F. Each ASCII character is sent separately as 1 start bit, 7 data bits, that is LSB, sent first, 1 bit for even or parity, no bit for no parity, 1 stop bit if parity is used, 2 bits if no parity is used. No parity. Longitude redundancy check, that is LRC, is used for error checking. One advantage of ASCII code is that it allows time interval of 1 second between two characters without causing an error. Later time interval suggests that error might have occurred in transmission. Message start with A colon represented by ASCII 3A hex and CRLF defines carriage return line feed ASCII 0A and 0D to specify end of frame. Figure shows the Modbus ASCII message frame. Start contains 1 character, address is of 2 character, function is of 2 character, data is of n character, LRC checks is of 2 characters and end is of 2 character, that is CRLF. Next is RTU transmission mode. Coding system. 2 hexadecimal characters are contained in each 8-bit field of message. 8-bit binary with 2 hexadecimal characters 0 to 9 and A to F. Each ASCII character is sent separately as 1 start bit, 8 data bit, that is LSB sent first, 1 bit for even or parity, no bit for no parity, 1 stop bit if parity is used, 2 bits if no parity is. Cyclic redundancy check, that is CRC, is used for error checking. Each message is transmitted in continuous frame. Time delay causes error. Greater character density of RTU mode allows better data throughput compared to the ASCII mode. RTU doesn't have any specific character to represent start and end of frame as in ASCII. RTU uses T1, T2, T3, T4 to represent the band rate being used in the network at start and end of the frame. Figure shows the Modbus RTU message frame. Start consists of T1, T2, T3 and T4. Address of 8-bit. Function is of 8-bit. Data of n into 8 bits. CRC check is of 16 bits and end is T1, T2, T3, T4. Modbus address. Modbus address begins with 8-bit address of target that ranges from decimal value of 1 to 247. 0 is used for specifying broadcast address. Each query has address of specific slave defined in frame format for both modes. Address field contains 2 characters in ASCII mode and 8 bits in RTU mode. Modbus function. Function defines the action to be taken by the message. Modbus function field contains 2 characters in ASCII mode and 8 bits in RTU mode, having decimal value ranging 1 to 255. For example, Modbus function 0x02 read input status, Modbus function 0x11 report slave ID, etc. Modbus data field. Data field defines the application level information to be used by Modbus function. When data size is variable, byte count needs to be specified at the start of the data field. Summary of today's lecture. In today's lecture, we have discussed the WPN technologies for IoT, in which we discussed the near field communication, that is NFC, Z-Wave, BLE, that is Bluetooth Low Energy, BACnet protocol, Modbus. Thank you.